Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Model 025 Basic Circuit Theory, Part 2. Please follow me in this lecture series by subscribing to my YouTube channel at https://youtube.com/@Ndinechi Please like and share with your mates in other universities. Drop your comments at the comment section, or you can reach out to me using my email address. I would also like you to listen to my lectures on applied electricity for beginners at my channel using Model 020, and the link is as shown. I've also done lectures on electromagnetism and magnetic circuits, which is an introduction to this circuit theory we are treating today. You can listen to that lecture on Model 021 when you get to my YouTube channel, which is termed Engineering Lecture Series. Of course, you can listen to part 1 of this lecture we are looking at, where we treated things like Ohm's law, Kirchhoff's voltage and current law, the Superposition Theorem, so that you will begin to appreciate and understand the current part 2 we are looking at. In part 1, we went straight to look at the Ohm's law, Kirchhoff's laws, but today we are going to start by going through some definitions you will be meeting insofar as you have something to do with electric circuits. And the first amongst them is the circuit element. We say that any individual circuit component, such as inductors, capacitors, generators, resistors, and so on, with 2 terminals by which it can be connected to other electric components, is called a circuit element. And a branch is any group of circuit elements, usually in series and with 2 terminals. A potential source is a generator which maintains its value of potential independent of the output current. It is important for you to know this decision. An AC, an alternating current source, will be indicated by a circle enclosing a wavy line. If you see a circle with a wavy line inside, automatically it tells you that it is a potential source. Of course, the current source is also a generator which maintains its output current independent of the voltage across its terminal. The current source will be indicated by a circle enclosing an arrow to reference current direction. So in a circuit, when you see a small circle with an arrow inside, it automatically tells you that that is a current source. And we say that a current source is a generator which maintains its output current independent of the voltage across its terminals. Now, network and circuit. An electric network is any possible interconnection of electric circuit elements or branches. An electric circuit is a closed energized network, and a network is not necessarily a circuit. Very important. So when we use electric network, electric circuit, they don't really mean the same thing. An electric network is any possible interconnection of electric circuit elements or branches. When we talk of electric circuit elements, we are talking of resistors, capacitors, inductors, those two terminal components. We say that an electric circuit is a closed energized network, while a network is not necessarily a circuit. Example, when we look at our two-port networks, we will begin to see things like T network, which are not necessarily circuits. Lumped network. Any network in which physically separate resistors, capacitors, and inductors, that is the circuit element, can be represented is called a lumped network. And any network in which resistors, capacitors, and inductors cannot be electrically separated and individually isolated as separate elements is called a distributed network. A transmission line is an example of such a network. When we go further to look at our two-port networks and transmission lines, you see that if you take a finite element, you can get inductors, capacitance, and other energy associated with it. And when you start analyzing that, you see that you cannot really call it a circuit element. So such electric networks are called distributed networks. A passive network is that contains only circuit elements without any energy sources in them. So it doesn't have energy source. You call it a passive network. If it has energy source, you call it an active network. So an active network contains energy sources together with other circuit elements. Now, this circuit element could be a linear element. So when we talk of a linear element, we say that it's a circuit element is said to be linear if the relationship between current and voltage involves a constant and a constant coefficient. Example, when we talk of Ohm's law, V equals IR. Or say, when you now make reference to inductor, you say that V is equal to L, which is the inductance, di dt. That is change of current with time. Or V is equal to 1 over C integral I dt. So if you do a plot, you see that It's a kind of linear element. A linear network is one in which the principle of superposition holds. In our last lecture, that is module 025 part 1, we treated superposition theory. A linear network is one which is a non-linear network is one which is not linear. Now, before we start our lectures proper today, we have to look at what I call self-test assignment. I expect you, just 5 of it, to quickly, in the comment section, just test yourself and answer this. The first one says, the current in a fixed resistor is dash proportional to the voltage across that resistor. 2, if the voltage across a resistor is held constant, the current in that resistor is dash to the resistance. The formula which gives the mathematical relationship between IV and R in a closed circuit is I equals what? 4, the equation in 3 is called what? 5, if the voltage across a 10,000 ohm resistor is 250 volts, what is the current in that resistor? So quickly, after the lectures, test yourself and see if you can answer these questions. If you can, it means that the part 1 of this lecture is well understood by you. If you can't, please, you have to go back and listen to the lectures. Give your answer in the comment section that we go through and, reply to all the people that got the answers correct and supply the answers to them. But that will be only people that attempted it. And very important to note these self-assessment assessment or assignment, because of no person will know the nature of the exams. Let's go on. Today, we are going to look at properly the mesh and loop analysis. A set of branches forming a closed path with the omission of any branch making the path open is called a loop. Mesh must not have any other circuit inside it. Loop may have other loops or meshes inside it. Node or junction are also equally used each time we are doing circuit analysis. So a terminal of any branch of a network common to 2 or more branches is known as a node. Voltage of any node with respect to a datum, that is reference point, or ground, is the node voltage, at times known as the nodal voltage. Voltage between any pair of nodes is the node pair voltage. Mesh, at times called loop analysis. Let's look at it very well now. Please make sure you understand this, because it will form the basis of you doing any network analysis. Kirchhoff's voltage law is the basis of mesh analysis of electrical networks. In the next one, we will see that it is the Kirchhoff current law. We, of course, know the two laws, Kirchhoff's voltage law and Kirchhoff's current law. So in mesh analysis, only the voltage input sources are present. A mesh is a closed circuit path that does not cross any other circuit path. The direction of mesh currents are chosen to be clockwise. The generalized mesh equation can be written as, in matrix form, Z times I equals V. We see an example very quickly. Look at this fig 1. We say that it is a mesh network. Just like we said, you see two voltage sources, VA and VB. So VA, which is a voltage source, generates a current, which we call the IA, and that current passes through the resistor R1 and the resistor R2. Now, on the right, you have another source, VB. That VB tends to generate IB, current IB, which also passes through R2. So you see that while VA is supplying current IA coming from top to down, VB is having current IB, which is going from down to up. Now, let us do an analysis of this circuit, because when we know the values of R1, R2, and R3, we should be able to find the current IA and IB flowing in the two meshes. Now, say, assume that the mesh has currents as shown in fig 1 above, that is current IA and IB, using Kirchhoff's voltage law. VA will be equal to IA R1 plus IA R2 minus IB R2. Can you see that? Because IB is flowing against IA across resistor R2. So the voltage developed across R2 will be resultant of what VA is producing there and what VB is producing there. So that gives us equation 1. So if we now look at that equation 1, we can see, of course, open the bracket and we see equation 3. But then let us look at mesh 2. Mesh 2 is the mesh that has VB. So we see, with reference to R2, that VB is supplying a current which is against the current being supplied by VA. So we quickly term it minus VB. So we say that from that circuit, we'll be producing IB R2 plus IB R3 minus IA R2. I want you to see that mesh 2 again. If we are looking at mesh 2, which is the mesh that contains VB, you see that IA R2 is against the way VB is supplying. That is why equation 2 is having minus IA R2. So, of course, if we expand equation 1, we get equation 3. If we expand equation 2, we get equation 4. I want you to convince yourself that in equation 2, if you bring out IB, it becomes IB into R2 plus R3, and of course, minus IA R2. So equations 3 and 4 can be solved using simultaneous equations when the values of R1, R2, and R3 are specified. And when you do that, you'll be able to obtain the values for IA and IB. So now this mesh can go on from mesh 1 to 2 to 3 to 4. If you follow the same pattern, you'll be able to get the equations for all the meshes. So if we consider the general network with Zi, when we say Z here, we mean impedance. As we progress, we start detaching ourselves from just using resistances, because in the real sense, pure resistances do not exist. That terminals you use to connect has some flux linkages, and that flux linkages must affect the value of the resistance. So we start looking at resistances in form of impedances that have real and imaginary values. And when we start looking at that, we call them impedances. So it will no longer just be, only the real part. You start considering the imaginary parts. So we say if we consider the general network with Zi as the impedance, I've explained that what impedance is, and Vi as the voltages, where I is an integer, 1, 2, 3, and so on. So let's look at this mesh 2, fig 2, which is another mesh network. So if we consider mesh 1, mesh 1 is where we have the current I1 flowing. If you consider mesh 1, I'm using Kirchhoff's voltage law. You will have that V1 is equal to I1 Z1 plus I2 Z3 for now. It doesn't really matter the signs. When you finish computing, if you have negative sign as a result, it means that the current is the other way, not the way you took it to be. So, but here, mesh 1 is current flowing as a result of V1. So that current will flow through Z1 and flow through Z3. But at Z3, current I2 is opposing or flowing in the opposite direction. So we put the equation for mesh 1, which is V1 equals I1 Z1 plus, that should be I1 Z3 minus I2 Z3. Please take that correction. That equation is V1 equals I1 Z1 plus I1 Z3 minus I2 Z3. Please note the correction. In which case, you can, bring out I. So you can now expand that to get equation 5. Can you confirm that? So it will give you V1 equals I1 Z1 plus, in brackets, I1 minus I2 times Z3. So if we consider mesh 2, you can see that mesh 2 here has no voltage source attached. So it becomes, the voltage source to it becomes 0. So like before, it will give you I2 minus I1 passing through Z3 plus I2 Z2 plus I2 minus I3 passing through Z4. Please look at that again to confirm. The mesh 2 is the one in the middle. If you look at it, I2 is passing through Z2, is passing through Z4, is passing through Z3. But if you look at Z3, I1 is opposing it. If you look at mesh 3, that is Z4, I3 is opposing it. So that is where we are having the minus signs. So you see it, I2 minus I1 Z3 plus I2 Z2 plus I2 minus I3 Z4. If you open up the brackets, you get equation 6, which is I1 Z3 plus I2 into Z2 plus Z3 plus Z4. So if we consider mesh 3, we can now see that V2, like before, we put the minus sign to show that the V2 is working against V1. At the end of the day, if it happens to be positive after solving, if it happens to be positive, it means that two of them are supplying together. If it happens to remain negative, it means that one is charging the other. That is the essence of using a battery to charge another battery. If you've taken your car, your battery to a battery charger, you will see that is using another generator to charge your battery. In other words, it's giving a higher charge than what your battery has. That is the picture we are trying to paint here. V2, V1 in a circuit. It's either two of them are reinforcing or one is charging the other. So if we look at the equations we have generated from mesh 1, mesh 2, and mesh 3, so we can now draw, a matrix to show what is happening. Just like at the beginning, we said that, using the Kirchhoff's law, V is equal to IZ, and they can be put in matrix notation. So that is what is happening here. So on the left, we have our matrix V1, V2, V3. Then we have our Z1 plus Z2. That is what we have in the equations for V1 minus Z3, 0, then minus Z3, Z2 plus Z3 plus Z4, that is from equation 6, then minus Z4, 0 minus Z, then Z4 plus Z5 times I1, I2, I3. So you have formed the general mesh matrix notation. So say if we use the matrix notation, you see that what we have there is like Z11 plus or minus Z12 plus or minus Z13, then plus or minus Z21 plus or minus Z22 plus or minus Z23, then Z31, Z32, Z33. This is matrix notation. So we say that for a generalized three-mesh network, V1 is equal to I1 Z11 plus or minus I2 Z12 plus or minus I3 Z13. For V2 is equal to plus or minus I1 Z21 plus or minus I2 Z22 plus or minus I3 Z23. And V3 is equal to I1 Z31 plus or minus I2 Z32 plus or minus I3 Z33. We want to limit ourselves for now to 3 by 3 matrix. It can go on to 4 by 4, 5 by 5, any length of matrix, but we are looking at the one that we can easily solve to get an answer and understand what is happening. So, node voltage analysis. Let's look at it, then we look at some examples, solved examples, so that we appreciate what we are doing. So, say a node is a point in a network common to two or more circuits. It employs the Kirchhoff's current law. The node voltage method consists of finding the voltages at all principal nodes with respect to the reference node. If you look at this fig 3, you see node 1 where we put 1 is a node because you see you have a circuit coming from Z1, Z3, and Z2 joining at that point. So it's a node. The same thing at point 2 or node 2, Z2, Z5, and Z4 coming at that point. So, say at node 1, look at that node 1. If we take V1 at that node 1, it will be V1 minus Vx all over Z1. Let's get it. V1 minus Vx all over Z1. That is what will give you the current flowing across Z1 plus V1 over Z3. Look at it. V1, Z3 is from V1 to the reference point, which is the ground, while Z2 is between node 1 and node 2. That is what we have, V1 minus V2 all over Z2. We say is equal to 0, equate it to 0. So if we rearrange that equation, we bring out V1. See, V1 is having Z1, Z2, and Z3 under it. So if we bring out V1, it becomes V1 into 1 over Z1 plus 1 over Z2 plus 1 over Z3 minus V2 over Z2 or V2 into 1 over Z2 and Vx into 1 over Z1. Sorry, that's equation 8 is Vx into 1 over Z1. So, but if you look at that, you see that it appears as an admittance because we know that the inverse of impedance is called admittance, denoted by Y. Therefore, we say that equation 8 becomes V1 into Y1 plus Y2 plus Y3 minus V2 into Y2 plus, it could be plus, it could be minus, but minus Vx into Y1. That is why I told you that in that equation 8, that Vx 1 over Z2 should really be Vx 1 over Z1. Don't mind the typographical error. So at node 2, you do similar thing, V2 minus V1 all over Z2. Let's quickly understand that. In node 2, V2 minus V1 all over Z2, V2 over Z4, and V2 minus Vy over Z5. That is what you're having. So if you rearrange it to have it as V1, V2 equals Vy over that, then you have a general formula, just like we have in the matrix before, that we give you Y11 V1 plus Y12 V2 plus Y13 V3, we give you I1. V21 V1 plus V22 V2 plus V23 V3, we give you I2. V31 V1, Y31 V1 plus Y32 V2 plus Y33 V3, we give you I3. So it becomes general, so that immediately you generate the equations, you plug it in the matrix notation and solve for your I1, I2, I3, I4, whatever. So we say where Y11 is the self-inductance or the self-admittance of node 1 given by the sum of all the admittances connected to node 1. Similar definitions hold for Y22 and Y33, whereas Y12 is the mutual admittance between node 1 and 2 and given by the sum of all the admittances connecting node 1 and 2 and has a negative sign. Similarly, Y23 and Y13 have negative signs. A current which drives into the node has a positive sign, while the one that drives out has a negative sign. So we say, note usually that Y13 will be equal to Y31 and Y23 will be equal to Y32. So let's look at an example. Just like the first equation we have, say solve for I1 and I2 in Fig 4 by nodal analysis. So this is a circuit that has 10 volts on the left, 15 volts on the right. It has the 10 volt has 5 ohm internal resistance, but connected to a 2 ohm resistor, supplying current to 3 ohms. And on the right, you have 15 volts also supplying current. Now, if we take that node A, you can see where A is. If we take node A, it becomes VA minus 10 all over 2 plus 5, because this 5 is taken to be the internal resistance of the 10 volt generator. And to the right, VA minus 15 all over 4, and to the reference point, VA over 3. That is what you're having. VA minus 10 all over 2 plus 5, which is 7, plus VA over 4, VA minus 15 also over 4. So if you solve for VA in that equation, you get your answer to be 0.726 VA equals 5.18, in which case VA is equal to 7.13 volts. Therefore, I1 will be equal to 7.13 minus 10, that is if you take it back to that equation, divided by 7, which will give you minus 0.41 ampere. And I2 will be 7.13 minus 15 divided by 4, which will give you minus 1.97 ampere. Now, your currents are having negative signs. So, if you look at it, it means that the direction which we said these currents are flowing are really not the direction they are flowing. You see that we put that I1 is flowing to the left, I2 is flowing to the right, but when we got two of them to be minus minus, automatically means that the two currents are flowing towards the junction A. In other words, the current flowing through I3 will be equal to the sum of I1 plus I2, because it means now that the current, the 10 volts and the 15 volts are supplying current to the 3 ohm resistor. So now I want you to look at this. In our last lecture, we looked at the Thevenin's equivalent circuit. So this circuit you are looking at, Fig 5, is very, very simple, but you have to really understand how it works. So we say, take it home, do it an assignment, and submit. So consider the circuit of Fig 5, where V is equal to 160 volts, R1 is 30 ohms, R2 is 270 ohms, R3 is equal to 500 ohms, and the load resistance is equal to 560 ohms. So in the equivalent Thevenin circuit, assuming the internal resistance of the supply is 0, what will be the Thevenin voltage, the Thevenin load, which is RT, and the load current? Please look at this and see if you can solve it. If you cannot, let me know. So thank you for listening to these lectures. We have one more lectures quickly and probably get together to solve them. Thank you for listening.